Hello, Nick. Thanks for being here.
Yeah, thanks for having me.
It's great to catch up. I really enjoyed catching up with you at the section leading reunion a few weeks ago, and sort of look back at our time, being involved in CS education, and it's just a great chance to geek out about these things with you. As
For sure.
sort of someone who's like who went through it at the same time as I did, as I fell in love with these concepts. I wanted to ask you what was your CS journey like?
Let's see. I had done a little bit of programming before I got to college, which is how I knew I was interested in it, but I didn't know really whether I wanted to major in it or just do something else involving programming. So I think it wasn't really until I got to college and started taking more programming classes that I was like, hey, I really do like this stuff, and I want to do more of it.
Hmm.
And also, same thing for teaching. I didn't have very much experience with that at all, and just tried to apply for section leading because I realized that I had a lot of excitement and energy, like when I learned something to share with other people, and so I gave that a try. But it was really just kind of I learned as I went what I liked and how much I enjoyed it. And then I just kind of kept pulling the strings on that and TAing and
Hmm.
continuing to do teaching stuff and yeah. So hindsight is 2020, but a lot of the stuff as it went was very much just kind of following things that kind of seemed interesting to me at the time.
And what about it made them interesting? So what aspect? It's a big, field. It's there's so many ways that it can be manifested into sort of your personal preferences. What about it spoke to you first?
I really liked um, learning about how a lot of the things that we took for granted worked. I think that's probably what drew me to the systems track, which is a lot of implementation of things that we take for granted, like compilers or operating systems or the internet, which I learned in my networking classes basically held together by a bunch of duct tape and straws. And it's kind of amazing that it actually works. But it is cool to see, what makes it work, because a lot of these things that we take for granted, we think are like magic. We don't know how they work. We don't know
Hmm.
what really makes them tick. And so I think it kind of came from that, of this interest in just saying, how does this stuff work? Like somebody had to build this, like somebody had to make these things.
Hmm.
How did they do that? And so being able to learn more programming, to be able to learn how to implement more of these things, I think that's kind of what kept drawing me in.
Hmm. Did you do the systems track?
I did systems undergrad, and then I switched to the AI track for my co-term masters.
Mm, I see. No, no, it is. I mean, like, it is fascinating, like, just how many layers of abstraction exist from, somebody using these digital services today, something like TikTok, which is already like so far, it's like above like layers of like social engineering and, all these concepts that come into it to something systems level where you're literally deciding like if using one more bit of memory is worth it for each, I don't know, like inode in a file system, right? uh, and so I think it's awesome. Was there something else that drew you to it? Was it just the how was this world we sort of see unfolding work? Was there another component to it, or was that mainly it?
There was also, I think, an aspect of just being able to learn how to use this tool that is extremely powerful and I guess that kind of goes into this cliche territory of how powerful a tool it is. But I really realized that, where when you learn how to write the software, you can basically go out and make so many different things on a computer that you have access to, and you can contrast it to a lot of other things where you need a computer, but beyond that, your imagination can kind of just run wild and make whatever you want. So there have
Hmm.
been so many times over the years where, outside of class or just for some personal use, I've been like, oh, I have to do this task or something, and I feel like I spend so much time on it, and I'm like, wait a minute. I can write a program to do that, and again, it sounds kind of
Hmm.
stereotypical. And, there's the whole debate about whether the time you put into writing a program to do something actually ends up saving you time versus just doing it and not spending, the hours debugging it. But in the end, it's always just gives you this kind of empowering feeling of like, wow, this is cool. I can craft these tools to do all these amazing things because I have this skill.
Hmm. But you touched on a subject that I think is like maybe not. addressed enough in like computer science circles and programming is like this idea that you might get fixated with solving a problem with programming or computer science, and then you're sort of like, I want to do this for the intellectual pursuit. Um, and also, maybe just in general, if you do programming for a living, you find yourself in this with this very experimental cycle loop type of process where you write some code, you test it, you see if it works. It probably doesn't. It crashes somewhere where you didn't expect, and then you're sort of in this head banging sort of cycle until you reach nirvana, and so it all works and it does what you want. So how would you describe to somebody who's like not familiar with the development process? How would you describe um, um, getting into it, or sort of like approaching that cycle?
Yeah, I think that process is the real core of computer science, and it's funny because it's not something that's unique to computer science. This idea of just this loop of problem solving. Like you run into a problem, you have to systematically investigate what's happening, arrive at a solution, fix it, right? And then you encounter more problems later and you fix it. That's not something that's unique to computer science. It comes up in every discipline. But I think computer science has it as such a core part of the development cycle. I don't know if I don't want to say that's because programming is more error prone, because I don't think that's necessarily true. But I don't know. It just like that debugging process has become synonymous with computer science, which is interesting because at least when I started programming, you sort of get maybe like I would think about this mindset where I would say, oh, well, but when I'm a much, much better programmer, I won't have bugs, right? Like there won't be debugging anymore because I'll be a better programmer. And of course, that's not true, right? But you think about, oh, maybe coding is 90% coding and 10% debugging. But in reality, it's more like 50-50 at least, where you're spending some time writing code, but then you're spending a lot of the time debugging it. But I think that debugging, it really just entails encountering a problem and having the reaction of saying, okay, I have this problem where it's not doing what I expect it to do. But I'm going to use the tools that I have to be able to like scientifically, kind of like, in science experiments where you have controlled variables, like you don't want to change too much at one time. You want to be like, okay, I'm not going to change too many things at one time. I'm just going to systematically investigate step by step to narrow down where the problem's coming from, which lines of code it is, so I don't have to look at the entire program. And then I'm going to print out values of things to see what's there that I don't expect. It's sort of like this interesting intellectual journey about figuring out where it is that what's in your head does not match what's on paper. And then, fixing it and convincing yourself that the change that you're making will actually fix the issue. It's not just a haphazard fix and you're not exactly sure why it works. And then, getting that satisfaction of, hey, I learned something new. Like it's this learning process where when you encounter a bug, it means, okay, there's some disconnect maybe between what I think should happen and what's actually happening. And by fixing it, you're like, okay, now I better understand what's really going on. So every step of the way, you learn a little bit more.
Mm-hmm. No, and I think it's important to talk about this stuff because I think a lot of the deterrence to people really like leaning into computer science is that feedback loop can be a bit intimidating, right? Sort of like you might be, bugs can come in all shapes and sizes, but like, you could be running into really bad stuff that crashes the program, crashes, the computer even. And that puts you in like if you're trying to get really fast at these cycles, it really requires this sort of patience with oneself, beginner's mind, sort of like I'm gonna be okay if I just try it again, like but it's very easy to get in your head about it and be like, oh my gosh, I can't see it. It has to be somewhere, and sort of like this sort of like inner sort of strength to do it. So I appreciate you elaborating on that. What
Yeah.
about before you write code? What about the stuff that happens in the brain when trying to solve a problem? That before you sit down to write.
Yeah, it's also something that's interestingly not, unique to this discipline, but I think CS has a interesting, how powerful of a tool it is to let you take whatever's in your head and put it on paper. So like even beforehand, it's okay, how do I break down this problem into smaller pieces? What unexpected cases are there going to be that maybe I'm not considering? What are the use cases? What, if I kind of think through the possible complexity points or things that are going to potentially cause issues in how I implement something. Like, okay, if I'm storing a lot of data, how am I going to store it? What format is it going to be in? When I read it in, is this going to be a really expensive operation to process the data in the way that I want? Like, is it going to take a really long time? Are there ways to make it more efficient? Those are a lot of things that you can kind of sketch out before you even start writing any code. And actually, that's, in my opinion, that's where a lot of the magic happens. Like when you start writing code, the goal is you already have, you can't possibly anticipate everything that's gonna pop up when you actually start implementing it. But you can have a pretty good roadmap in your head from the get-go about, okay, I kind of have a visual in my head or on paper, or I've written it out or spec'd it out, where I know what files what code I'm going to need to write in what places, what functions I'm going to have potentially, what the interface is going to be like for whoever's using it, what the output's going to be, and potentially accounting for different edge cases, unexpected inputs. A lot of that stuff, that roadmap, having it down from the get-go is really, really useful. And that's where the pseudocoding kind of terminology comes in, where it's like, hey, before you write, let's write some pseudocode. Let's write some higher level, just kind of get your thought process down on paper, because then you can reference that as you actually start writing. And I think that brainstorming thought process is really, really important.
Mm-hmm. And there might be creative roadblocks there, even, right? Like even in the how do I well, you said it, like decompose this big problem into the smaller subparts. I guess this is as good a segue as any. Like, what are some of the most valuable lessons that you've learned through computer science, whether as somebody learning it or somebody teaching it?
That's a good question. There are a couple things. The first one is, I think, going back to that debugging question that you asked about, that debugging mindset, I think, pays off in a lot of places outside of computer science. Just that systematic problem solving approach, where like whenever you encounter something that's not working or something that's broken or some problem that you have, just systematically gathering information about what's happening that you don't understand, and then eventually hopefully reaching a solution to that problem, and just having that determination and that confidence of like, no, I do feel like I have the tools to get to the bottom of this. Maybe I don't understand what's happening right now, but I feel like I have the tools to gather more information to the point where I will understand what's happening, and then I'll be able to hopefully solve the problem or understand at least what's causing the problem. So I think that's definitely been a big takeaway. The other thing, and this maybe comes from teaching more of the core classes that people take perhaps earlier in their programming journey, is how a lot of the underlying principles of computer science are, like when you distill them down to their essence, are just really broadly applicable, like decomposing a problem down into smaller pieces, that are more manageable, or explaining how computers work and realizing that there are a lot of metaphors and analogies in how computers work that are similar to how we think about how other systems work. So talking about when you have multiple things running at a time and coordinating between different tasks, right? That has a ton of parallels to how we as people coordinate. If we have a group of people, we're all trying to tackle a task. How do we split it up? How do we coordinate between those people? And so that kind of tying to scaffolding that we may already have in understanding other things in the world, I think makes it a very cool linkage in how applicable those ideas are. So I think those, there are many others that I could probably think of, but I think those are the main ones, is just, from teaching the material, seeing how much you can tie it to things that we already know, we already think about, we already, have to solve problems with. And that shows you how just applicable and valuable this field is. And then also the problem solving skills that you get from working through these things.
Do you happen to have specific examples of like these key moments of insight, or?
I think the close example I can think of is when I teach this operating systems class. There are a lot of times where, and maybe this is just because I'm kind of overly goofy, but I'll use a lot of acting out of things in sort of like humanizing or personifying different parts of how an operating system works. So when we talk about an operating system, it's this thing behind the scenes that the programs that are running on your computer are communicating with and asking it to do things for you. Like, can you load files from the file system, or can you can you run this other program for me, or something like that. And whenever we talk about these concepts in class, a lot of times I'll just like jump into bad acting mode, I call it, and just kind of act out like I'll pretend I'm the operating system over here, and then I'll jump over here and I'll be the program, and like talking back and forth and having this kind of communication channel. And I think that really, that personification of, that anthropomorphizing of what computers are doing just makes me realize how relatable a lot of these things can be if you really distill it down to its essence of like, oh yeah, if I'm writing, like when I'm writing these, we're teaching these multi-threaded programs where programs are doing multiple things at the same time, and one task maybe has to wait for another one to finish. I'll do this, acting out of different threads that are trying to make sure to coordinate with one another. And so there, I don't know, just a lot of these, when I think about how it can end up being relatable and how we talk about these concepts, I think about a lot of the like acting or analogies that I end up using in classes that say like, yeah, this is just like this other thing that maybe you can think about or imagine it just as if it was like this.
Mm-hmm. No, and I think that makes all the difference for CS as a learner to have those analogies to be able to hold your understanding of the world. I mean, one of the things that is tricky about computer science is that it's incredibly filled with um, um, initials and shorthand names and esoteric looking symbols of strings of characters, especially in systems when sometimes you find like these macros that are just like literally some number in hex. And but having a sort of like something more humane to compare it to, I think makes all the difference, especially when it comes down to actually being a citizen in these systems and like having to edit something in within, I don't know, hundreds of files, and having to trying to eke out some memory performance issues. And it makes it so much more accessible. And one of the things that is daunting about computer science in general is that just even getting started with like a dev toolkit, like installing Eclipse or installing, how would you even know to start there unless you had someone who's like sort of like talking to you from the land of the humans into this stuff, which is amazing. And I wanted to ask you sort of like, okay, we talked a little bit about on the programming side. What was the teaching journey like for you? So you said you applied to section leading, and how did that feel, and what did you start noticing in yourself and others as you did it?
Yeah, I think when I started doing when I started section leading, it was mostly a realization of how when I felt like it sort of connected well with how when I got excited about when I learned something, I would want to turn around and share it with somebody else, or help somebody else understand it. Like when you get that kind of satisfying, click in your head, want to turn around and say, hey, there's this really cool thing. Like you should, I want to tell you about this. Like, this is really cool. Once you kind of understand how this works. And that's kind of how I felt. And that's kind of what fed into my initial excitement for teaching, was especially section leading for 106A. It was the one that I did the most. The very first intro class with no prior experience required was just this excitement of, I get to help introduce all this stuff to people for the very first time. Like no prior scaffolding, no prior experience with any of this stuff. And that's a really hard challenge, but a really cool challenge, because it's like you start at square one and you help people build up that scaffolding from the very beginning. So I really like that, and being able to like show my excitement about it and hopefully get other people excited about it. And then kind of as I went, TAing more, taking on more responsibility. I head TA'd for 106A later on, which is a lot of managerial responsibility, and still a lot of
it's a big job. Yeah.
Still a lot of teaching, but a lot of managerial responsibility. And so I wasn't initially sure how I would feel about that, because part of it, I felt that I really wanted to stay with the direct teaching. Like, I want to lead a section, I want to help students directly in office hours. But I also felt like I really learned to enjoy that managerial aspect too, because you get to make a lot of the interesting behind the scenes decisions about the structure of the class and how the class is managed and run. And then I got a chance to teach 106A over a summer, which was kind of my first time just being able to really do a deep dive into just being able to focus on that rather than having a TA position alongside being a student and taking classes. So I think that summer was my first real full on experience of saying, wow, yeah, I could really see myself doing this, in a full capacity in some way. But I still didn't really see how that would connect with the future dots that kind of landed me where I am today.
I'm very curious. What were some of these light bulb moments? What was it that triggered those? Because I felt the same thing. Obviously, like there are some ideas in computer science that are just so beautiful and cool. I want to know what some of those are for you.
Um, I think the very first one, really going back to the debugging discussion, was that like problem solving process and helping people get into their flow in that problem solving process. I think back to like 106A when I taught people Carol, the robot in section, which is what we do before any programming at all. And even before you realize you're writing, what I guess people would say real code, although that definition is very amorphous, and I think Carol's just as real as anything else.
It is, yeah.
Yeah, but helping people see the, like, I think Carol is just such a great introduction to the problem solving process of like, okay, I have this robot in this virtual world and I need to move it around and accomplish these tasks, and it has all the same stuff in programming: debugging, breaking down a problem, all these things that are just so crucial and essential to the field, that I thought, like, just seeing that and being able to help people learn Carol after I had learned it, I think was maybe one of those light bulb moments. But beyond that, I think that I mean, in terms of things that I just saw and I was like, wow, this is just so cool. Like, I just like this. Just I get so much energy and excitement learning about this that I want to share with other people. When I learned more about how the internet works and all these different layers, and I don't know, I just felt like, so the way how it's, applications want to send data across the internet, but of course the internet is so complex, the system has to be broken down into smaller pieces. And when I took this networking class, you see how there are all these layers that build up on top of each other. So at the very bottom, it's the hardware layer that's just sending data between two nodes that are closer together. And then layers above that say, okay, I'm going to send it to something further away. How does it get there? And then layers above that are like, okay, what if the data doesn't make it? I have to resend it. How do I make it reliable? The layer on top of that is, well, the programmers don't need to know about how all the hardware works. Like, they just want to send some chunks of data, and having them do that without having to worry about the complexity in lower layers. I felt like that was maybe one of those moments where I saw the real power of breaking down a problem, is saying, well, there's this really powerful design idea where if you have these layers that build on top of each other, the upper layers don't have to worry about what the lower layers are doing, because the upper layers are just worried about their problem, and they can just take for granted the functionality that the lower layers provide. And of course, that idea is applicable in so many other things too, outside of programming, where we rely on other people, right? We don't, maybe if we have a task and we assign subtasks to other people, we don't worry about maybe the specifics or intricacies of how they accomplish that task, as long as they, complete the task, and then we take what they completed and then we use it for something else. So I think for me, that was one of those, like, wow, this is so powerful of an idea, and it lets us build these huge things, the internet, that you would never think would be possible to build, and they probably wouldn't be unless you designed it in this kind of systematic way.
No, that's one of my favorite. Abstraction, just the concept of abstraction, and even from something of ginormous scale like the internet to something super tiny scale like a helper function that you just reuse a bunch of times. So like a little snippet of code that you're going to be using a ton of times, instead of rewriting it every time, you sort of you cache it into a function. And you use that a lot, and you start sort of like leaning on your prior cognitive efforts. Sort of like you start getting leverage on your cognitive effort that came before. And I thought, like, the Steve Jobs quote of a bicycle for the mind really makes sense in that context, where all of a sudden you solve a problem, you don't need to worry about that problem again unless something in the environment changes, right? a library goes out of, there's a breaking change in a library, and sort of like something else in your abstraction you need to change. Um, and there are so many. Recursion is one of my favorites too. Like when I figured out recursion, I was like, oh my gosh. So you mean logic can consume itself and you can use a function from within itself? Oh boy. Um,
Yeah,
and
the interesting idea that I think it also links to is delegation. So like in real life,
mm,
I'm a really bad delegator. I need to be a better delegator where I need to delegate more tasks, away so that I can focus on other things. But um, decomposition is basically delegation. It's saying I don't want to spend brain cycles worrying about this. I want to rely on some other piece to accomplish this task, and I'm not gonna assume anything. I'm just gonna assume the what it does, like the output, not how it works. And then I can spend my brain cycles working on other things because I no longer have to worry about it. So, like the recursion example you mentioned, recursion is basically delegation to yourself, which is kind of a weird way to think about it. But you're essentially writing a function that uses itself. And so you're writing it while assuming that it will do what you expect it to do. But then, right, but that frees you up in just like in real life when you delegate, you no longer have to be paranoid or overly think too much about how this other piece is doing what it's doing. You're just like, no, I'm not going to worry about it. I'm just going to like trust in the process. I'm going to trust that it's going to do what I expect it to do, right? And then I can work on the system that I'm working on and trust that that piece is going to do what its job is.
mm-hmm. Well, actually, this brings up another idea that sort of like you encounter inevitably in your programming journey, where you go from this initial impulse of trying to solve a big problem by starting with immediate, minute tasks, um, say like very minute, very low level instructions to a problem. That over time you build this abstraction ability, so that you go from bottom up programming to top down programming, and then you sort of like start trusting your brain enough to hold these non-defined, or sort of things that are defined just in terms of an interface. Um, and I'm not going to worry about anything that's inside of this block. I'm just going to take it for granted and then go in. How you have so much more experience of seeing this through so many students, right? Like, how does it manifest usually? Like, what is the path from somebody who breaks, clicks and is like, okay, now I'm a top down programmer?
Yeah, it's a good question. I mean, I think a lot of it comes from the sizes of the projects that designing something top down allows you to build. So I think like as you're a programmer, as you're a student going through these classes, you're getting to be you're getting to more and more advanced classes with more and more advanced projects, and you start to get closer to this point where maybe you can't keep everything about a project in your head at the same time, right? You can't keep the entire design or every moving part of a system in your head simultaneously. It's too much. It's too complicated. And so if you implement it in a way where you're not breaking it down into smaller pieces, kind of from the top down, you are, you maybe it just becomes more and more challenging to build these more and more advanced projects. Whereas if you kind of decompose it and break it down into these smaller pieces, it allows you to just tackle things of complexity that weren't possible before. And so I think maybe it's just kind of from the student side of as you go through these more and more advanced classes, you need to be able to think in this way where you have to be able to break down a problem into smaller pieces. This is one of the things that we're trying to think more about how we can give people more practice with in this operating systems class I'm teaching, where it's like, if we give you this large task, a lot of times in industry, you're just going to be presented with this large task and there's no predetermined or provided way to break it down. And so you need to come up with, okay, what milestones am I going to have? How am I going to test that it's going to work at each step? If you just implement the whole thing from start to finish, it could get really, really messy, and you could have bugs that you never, impossible. You're already, groaning. It's like, the experience where you write hundreds of lines of code without testing it, and then you start testing it, and you're like, oh gosh, I have no idea where this problem could be coming from because it's such a complex system, and I can't reason about all of it at the same time. So I think maybe it's just this process of, as you are asked to build more and more complex things, your thought process changes to allow you to be better and better at implementing those more complex things. And I think decomposing is a key part of what makes that possible.
Mm-hmm. It's so interesting because I was, sort of thinking about what questions to ask you, I was trying to think about my CS journey, and I don't remember there being a particular moment where I switched. But I know I switched because now when I think of a problem, I definitely think, okay, I don't need to figure out the specifics of every last little thing. I just am going to, do broader initiatives, and then, very like just in time compile the moments that I'm, and it's crazy now in this conversation. I'm realizing just how embedded the computer science analogies and frameworks are in day to day discourse. And I think that's something that computer scientists often like fall prey to is like the CS speak, and I'm doing this right now. So I'm realizing um, it is fascinating as a cognitive tool, and obviously as creative tool of being able to implement logic and deploy it at scale on the world. And so all of a sudden, I mean, it is one of those truly beautiful ideas, and I'm not sure um, which other disciplines have that unique combination of logic, predictability, self-reliance, scale, and leverage as computer science. I
Yeah,
was going to ask
it's
you. Sorry, go for it. Go for it.
no. I was just gonna say it's. I sometimes I think about other similar engineering disciplines and how they maybe have different flavors of the kinds of ideas that come up in computer science. So like may seem kind of random, but they're constructing this new building near where I teach on campus, and so I walk by the construction site all day, and sometimes I'll think about like what constructing a building versus writing a program, and it sounds cliche, but there's this interesting thing that I was thinking about, which is when you're when you're building a building, you better have scoped it out ahead of time and wrote down exactly like what's going to happen and what the building's going to look like. It's not like you can maybe in programming you can scope out like most of it, but code is malleable enough that you can go fix it and modify it later, adapt it as you come across new things you didn't anticipate. I know very little about construction, but I'm guessing that's probably pretty hard to do with a building where you just start building it, and by the time you get to the fourth floor, you're like, oh shoot, we didn't think about this. Guess we got to like totally rethink our plan here. That's probably not gonna happen. So I don't know. It's just interesting to think about how these other fields, it's also the same thing, thinking ahead, breaking down the problem, all these things. But programming is very malleable and allows you to do things maybe that other fields can't. But vice versa, where if you're in construction or something like that, you really probably got to get the plan right before you even start the actual construction. So I don't know. It's kind of interesting to just think about how they compare.
Yeah, and back to it. I mean, once you start seeing the more abstract lessons of computer science, you see it everywhere. You see it in art. You see it in business. You see it in. It is an incredibly powerful tool. I was going to ask you. You mentioned industry. You mentioned trying to sort of like adapt the curriculum and adapt the pedagogy of CS to match expectations of industry. I know that CS106A, the intro class, has changed a lot since the time that we took it. How would you characterize what the relationship between CS education and industry is, and maybe should be?
Yeah, it's there's always been a lot of stuff that classes don't cover that you learn in industry or that industry uses, and I think that's when I think about how classes and industry kind of coexist or working in industry coexist. I think the first thing that a lot of people talk about is situations where you start working or doing something in industry, and there are things that you never encountered in classes that you need that are essential to work. And you can maybe pick those up as you go, but sometimes it's like, well, hold on, why didn't I learn this in class? Or I didn't see this in class before, but it seems pretty important in industry. So I think there's always this kind of push-pull relationship between what a class is supposed to cover and what the goal of that educational side is versus the skills that you need to succeed in industry. And so I think, there's always questions about it, like how many tools should we be teaching that are used in industry versus should we be focusing more on the process or the thinking or the more abstract, problem solving skills behind it. I think maybe a mix of both is good, but I also think like if you just focused on teaching tools, you'd have to constantly reinvent your classes because those are changing so quickly. Things become obsolete very quickly. And so, maybe it's better in other cases to just stick to the more the things that have a more lasting permanence, like these problem solving strategies and decomposition and design, all these things. Like these things are perennial ideas. They're not, they're not going to go away in a couple of years. So yeah, but at the same time, it's, thinking about, okay, we don't want to have a class that's, so high level or people just don't really feel like when they actually go and try to apply it in industry, like they have such a hard time because it's such a big jump to actually use it, or there are so many pieces that are missing. So I think it's a tough one to think about. But at the same time, I think that, the classes aren't just supposed to be job training. I mean, I think they're definitely,
Right, totally.
the goal are definitely to be way more than that. And so I think it's okay to have that gap to a certain extent where, yeah, there are going to be things that you learn in class that you can't learn in industry. And there are going to be things that you learn in industry that you can't learn in class. And by industry, I also am thinking of even personal projects or anything. It doesn't have to be you work at a job, but just building things or doing things outside of the class setting. I think both of those will teach you things that maybe the other couldn't give you.
And I was asking because, there are so many ways to climb this tree, and sort of like thinking of like the programming language that you choose to learn first. Or that you are made to learn first, right? So we started with Java, pretty quickly got some C++, and so meta, we also pretty quickly got the idea that, okay, learning a language is just part of the job. You're just going to be doing this all the time. Those languages sort of meant something in industry, 10-ish years ago. They're not the same as the current languages that are, sort of more top of mind, and so it's 106A moved from Java to Python. Is that correct?
Yeah.
And so there's that sense of adapting to, I don't know what the word is, like baseline maybe, is like this sort of like, or lingua franca type of thing. So programming languages is one side, just like, there are so many ways that you can adapt, and you could, these ancestral concepts like decomposing and whatnot could be taught in any language, right? Every language, by virtue of being, a programming language, will support these things. There are other also slightly different approaches. So we started with a, object-oriented approach, and then, which is perfect as you go into the systems to understand, oh, this is how memory gets allocated. This is how a compiler can reason around the longevity of objects. It makes sense in a certain way. There's also, functional programming as it, as a, other philosophical current of how to think about programs, right? How do you personally think about those two? And like, what do you think, an idealized, like a utopian CS curriculum, how would those sort of be entertained? Well, yeah. What a fitting example of something to debug.
Yeah. Just try turning it off and on again.
Yeah.
So we were talking about
programming and OOP. Yeah.
The programming languages and like syntax and all those kinds of challenges.
And sort of style of programming, I guess, or like what the centricity of the programming is about.
Yeah, well, I totally agree that the syntax is always something that is incredibly intimidating for good reason. How programming languages are extraordinarily picky with syntax, and unlike humans, where we can kind of get the gist usually of intent by when people say something, if they don't say exactly the right word or whatever. I do have to wonder if 30 years from now, are we still going to be programming computers by writing text-based commands in a file that we then save and then feed to a computer to like translate into a version of the language that the computer understands and then run it? Maybe we will. I mean, coding has been around for a long time. It still would. But I do think about, to your point about the intimidation factor of the syntax, whether there are, what other ideas there are out there about ways that we can ultimately convey our ideas to a computer. Because programming languages are incredibly intimidating, but as you mentioned, like with your work, there are so many programming languages, you're often not going to use just one. Once you pick one up, it's easier to pick up more because the syntax and the underlying ideas are generally the same. But just by learning a programming language, that's not really the full magic of computer science. It's the problem solving, right? The language enables you to translate your ideas to a computer, but it's the problem solving that really is some of that secret sauce. And so I think it's almost like the programming language is this incredibly intimidating part, but that's not even like the necessarily the coolest part. The coolest part is what it enables you to do. So so I do wonder about, are there graphical programming languages? And some of these ideas are already being toyed with, but like, are there graphical ways that we can convey ideas to a computer, or if we could program with natural language? I mean, that's, a lot of these ideas are pretty hard, but just ways that are more accessible. And there are examples that are already popping up, like automation tools, like the Shortcuts app on iOS is an example of programming. Maybe not the way that you would think about programming, but it is programming. You're instructing a computer to do something by building up the steps that it takes. And lots of other examples too. But there's, I just think about ways that we could make the tool more accessible, because ultimately the goal is, how can we effectively translate ideas we have in our head into a form a computer understands? Right now, the most widespread way to do that is we came up with a syntax, a programming language that is good enough for us to be able to write, but at the same time, it's translatable to a form a computer understands, which is this much lower level representation. But are there other ways that we could create even higher level? Languages have changed over time. Languages like Python are much easier to use than older languages. But are there ways that we could go even further than that and make even more accessible interfaces to programming?
No, I was saving it for last, but this is as good a segue as I'm going to get to talk about something like GPT, a GPT layer on top of programming. So I've been using GPT a lot, and some of those lessons are still required to use it effectively. You still have to be incredibly specific about what you want out of it, and sort of like guardrail and constrain it. And like I don't think we're there as it is right now in a chat interface to really, get some serious engineering out of it. But there are some really cool ideas coming up with like GitHub Copilot. Replit has a cool one too. I forget what Ghostwriter, I think it's called. And sort of like, we're going to see this evolution of what the IDE looks like, I think, in terms of what the actual interface is. And I was wondering if you had any sort of like, you're also in the thick of like an educational context where people are going to be using GPT to, for their own assignments and debugging and whatnot. So how do you think that world should be reasoned around?
Yeah, it's, no great answers here, or if there are, I'd love to hear them. But I think to your point, like you said, the core ideas and the problem solving and the design are still there. Like the critical thinking about how, what the program is doing and why it's not doing something you expect, or even, if it can help you write code, you still have to have this structure in your head about how the system is going to work and being able to put the components together. Maybe that takes on even more importance, because now there are tools that can implement the smaller bits for you, but maybe the overarching picture you have to still do, maybe for now. But that higher level design idea is still there, very much so. It's still very much a layer that writes code behind the scenes, so you can use it, but it's the fundamental layer, abstraction layer is still code. It's just maybe that it helps you write it, but it is very, very powerful. But I've been thinking about this a lot, because we're trying to think about ways to what the role of this is in CS education. It's like, okay, if you're teaching somebody programming for the first time and you're trying to help them write a Hello World program, for instance, you could go to ChatGPT and ask it to, hey, write me a Hello World program, and it could write it for you. But the process of you getting there, it's the process, not the artifact, where the magic happens, right? I learned this saying from another instructor who I think was a great point about it's the process of getting there, not just the result, right? And when you're working on a project, maybe the result is super important because you're working towards some thing you want to build. But especially in education, when you're doing assignments, for instance, the assignment is really about the process, not the artifact. The artifact obviously is important, and you want to be able to make this thing and it works, and you can have this thing you're really proud that you accomplished. but it's really what you learn along the way. It's like, the bugs that you have, it's like, yeah, it's a bummer to have bugs in your program, but you learn a lot from having to work through those. Like you come out of the other side better equipped and understanding what's going on. I sort of joke sometimes when I write a program, if it works the first time, I get paranoid because I'm like, I'm sure there's a bug in here somewhere. I just haven't found it yet. And then if it doesn't work the first time, I'm like, okay, there's definitely a bug in here that I haven't found yet. So it's like either way, there's stuff to learn here. But yeah, so I think it just highlights the ever increasing importance of the process. Not just the artifact. ChatGPT can help us get the artifact, and I also don't want to diminish the fact that it can also help with the process, and that you can ask it lots of questions. You can ask it for help in understanding things. So I don't want to diminish that aspect too. But I think we will still need, even if we can go to these tools and have them help us, it's going to accelerate our ability to make things even more, but we're still going to have to be able to think critically about what it's giving us, how that fits into some project we're making, whether it's correct, how we know what we need to ask it, like what code are we going to ask it to create for us. All these things are still going to be there.
No, and I think, as layers upon layers of services and social organization get built on this stuff, then it'll be even more important to review something that goes wrong, very low level in the system, right? So like you'll still probably need somebody who knows, exactly how this physical architecture is connected to the instruction set. And so that's how you could get, like, for cybersecurity stuff, like that would be still super important. And I think a lot of that stuff is still very much like the seasoned veterans will have it, and people who are in the trenches of these systems will know, but not necessarily, like, as you get abstracted away, like most people will probably be oblivious to them, but it would still be just as important to keep them in mind, right?
Yeah, that's the thing is the goal obviously is to have as many people be able to have this skill as possible, because of its utility and its power and usefulness for people. But that's going to probably require coming up with newer and better and more accessible tools for people to do that. And so, yeah, there'll probably always be people writing code, and there's still languages that aren't maybe widely in use anymore, but there's still tons of code in those languages that people still need to maintain, develop, build. There's always going to be a need for that, probably for a long time. But as we continue to grow the number of people who can tap into the power of these tools, it's going to mean we're going to come up with newer, bigger, better ways to do that. And so the population of people who can do this is going to grow, and the percentage of people using maybe other different tools maybe will change over time as we invent new things. But yes, a lot of these things are, they've been around for a while for a reason, and they'll probably remain around for a long time to come. But it doesn't mean that there'll also be other ways that we could make it even more accessible.
What's your favorite programming language?
I like the high level nature of Python. I think Python is a really fast way to iterate on something, get it up to speed. Although sometimes there's sometimes I like the feeling of having a little bit more control over exactly what's happening with a language like C++ or I don't know, maybe I won't go to C, but but it's sort of like a stick shift versus automatic car, where it's like, I don't know, there is when my parents talk about it, like, hey, there is a nice feeling about having a little bit more like manual control over exactly what's happening. But I do really like the flexibility and ease of Python. I mean, it really, it's a great example of how languages have adapted over time to get slowly closer and closer to the higher level ways that we think, and it lets us express our ideas in ways that are closer to how we think. I mean, it's still a programming language, so there's a long way, there's a lot of things that maybe we don't think in that way, but it gets closer to that, and I appreciate that, because the closer you can get to the way that we think, the less cognitive work we have to do to translate our ideas into some syntax, and that translation process is where the bugs and the issues come in.
Python is awesome. I mean, and it's relatively concise too. Not something like, Java is gigantic in terms of the spread of libraries that you have to cover to be proficient at it. Python is actually relatively compact, and you can get all the way down to the compiler and know what's going on pretty easily. I would say that's something that C has in common, except C has like if you want to get to the higher level of abstraction that Python provides, you're going to be doing a lot of really scary, crazy stuff in C, right? Like, but there's something to be said about I don't know that you can really appreciate memory, and like the gigantic, like we take for granted things like assigning a number to a variable in any programming language, but or constructing an object, a person object or a company object. But there's so many layers of stuff, even in just like getting the computer to accept that instruction. um, that is fascinating. I don't know if you see that without something like C, where you're dealing with like, oh my gosh, I'm like, you have to, everybody should go through a segmentation fault at one point in their lives.
Well, that's the funny thing is because the third quarter class we teach 107 teaches C, or it's taught in C. I am careful to say, like, it's not.
I like that.
Yeah, I mean,
like
it's not necessarily a class that teaches you a programming language. I mean, you learn a programming language over the course of the class, but the primary goal is not to teach you this programming language. It's to, the programming language kind of fits the course material goals that you're trying to cover. So it's sort of like 106A is taught in Python, but you don't take 106A just because you want to learn Python. You're learning programming, and it happens to be in Python. But, it's not, the primary goal is not to teach you everything about the Python programming language. But 107 uses C, and, the messaging of that class is not, oh yeah, after this, you're just going to be writing code in C all the time, definitely every day, you just, C is just such a versatile language. You can use it for anything. I mean, that's clearly not the messaging there. So a lot of people justifiably ask, well, then why do I need to know C, right? If it's this low level language, it seems like there are much higher level alternatives today. Why do I need to still know C? And sort of to your point about a lot of the things that higher level languages like Python do for you, it can just help you better understand and take into account those things that it's doing for you, right? You can understand, even though you're not writing code in C, you're writing code in Python, you're like, oh, okay, but I know what complexity this really entails in order for Python to do these things for me that I'm asking it to do. I know how memory really works, and I know how you can pass data between functions and not have it make copies. A lot of these things that Python kind of abstracts away, you can still be appreciative and understand the complexity that it's abstracting away, and that can help you even if you're implementing at a higher layer.
Mm-hmm. What would you say are some of the biggest differences between the dynamics of teaching something like 106A versus something like operating systems? Like, what do you think in terms of student profile, in terms of you mentioned like the acting out that you have to do. What are some of the other differences there?
Yeah, the people are definitely at a different stage in their computer science journeys, which is really cool to see. I mean, you see these different data points as people kind of go through, and they're coming into 106A and learning programming for the first time, and learning their first programming language. And by the time they get to CS111, which is the operating systems class, they have seen multiple programming languages. They've gotten lots more debugging programming experience. They've used a terminal, which they learned in 107. And I think the biggest difference is that in 106A and classes that kind of lead up to 111, the primary focus is really learning programming techniques, like techniques that you can use to write programs that you couldn't write before. 106A teaches functions and variables and parameters and all these things. 106B, the class after it, teaches data structures, maps, sets, vectors, teaches recursion, pointers. 107 goes deeper, teaches pointers, memory, lower level memory manipulation, bits, bytes, all these things. And then you get to 111, and 111 still does cover some of that. Like, you learn about how to write multi-threaded programs. You learn about how to write programs that can spawn other programs or processes. But I think another main focus that's unique to 111 is it's also really focused on, even its primary focus is on saying, hey, you've built up these programming skills to this point. Now we're going to kind of pivot and not focus on developing kind of specifically the programming side, but show you these cool designs of how a system in the real world works, specifically operating systems. And you can use your programming skills that you've developed to this point to actually implement parts of that. So it's sort of like saying, hey, actually, you have a lot of these awesome skills that you built up to this point. Now you're going to use them to implement this real world system that maybe you didn't think you could implement, but you can because you have these awesome programming skills that you built up to this point. So I think the approach to 111 is different because the lectures are much less about showing code, about how to learning these kind of coding techniques, and more about, hey, today we're going to talk about how this aspect of an operating system is designed. We're going to go through the design. We'll talk about the trade-offs, the pros, the cons, how virtual memory works, how a file system saves your files to disk. And then on an assignment, you're going to go and you're going to implement those things, and the coding part is really you taking the design that we've talked about and then go and implement it yourself on these assignments. And so I think that's a different kind of structure than where students are in prior classes.
Mm-hmm. And that sort of is more similar to what you get in industry too, right? You're not spending time actually looking at code in a team meeting. Very rarely do you actually look at code. But you do just, design like, okay, this is what the interface is going to look like. This is what the API is going to be. This is what the contract is going to be. This is what the bigger system is going to look like. And then you divvy it up into, teams of up to, I guess, 20 people of each person tackling a component.
Yeah. Or, and if you're learning new programming techniques, which happens all the time, you're learning it in service of then using it to implement this system or thing that you're working on. And so I think that that structure is similar to 111, where the real primary goal for the class is to say, hey, we're going to apply your programming skills to be able to implement this larger system that you can see that you can actually implement yourself.
That is great, Nick. I have one last question. What are some of the misconceptions you've seen, throughout your years in computer science about computer science?
I think we've already hit on one, which is maybe the one I had about debugging and the presence of debugging and problem solving in coding as you become more experienced. If the expert programmers don't have bugs. They're just coding all the time and they get it right on the first try. And maybe that's part as you become a better programmer, you do get better, and maybe the kinds of bugs that you run into are different. Right? Maybe the kinds of bugs that you run into in 106A are different than the kinds of bugs you run into in 111, for instance. But everyone's debugging. I mean, everyone. I'm debugging stuff all the time. And again, maybe not the same kinds of bugs that I was debugging when I was earlier in my programming journey, but that debugging process is a constant. And I think that's, when you see people, it's like, oh, I have a bug, like that's embarrassing, or that's bad, or I shouldn't be having bugs. It's like, no, this is a part of the process. This problem solving is a part of the process. And every chance you get a bug is a chance to, is to learn more about what that disconnect is between what you think should be happening and what's actually happening. I also think that there's a lot of, and I've seen this kind of as I've tried to become a better teacher over time. There are a lot of ways that you can tie computer science concepts to make them more widely applicable, like the metaphors that we use, or the acting out, or all those things where you can take some idea that maybe is a very technical concept and in the weeds, very nitty gritty, but there are a lot of ways that you can frame it in a much more widespread kind of adaptable way where anybody can pick it up, even if they don't know the exact nitty gritty of some details of some concept. I think this is a challenge I face a lot in 111, where it's like, a lot of these people are not going to be going into systems. Maybe they're going into other areas. Maybe they don't need to know about all the nitty gritty specifics of advanced operating systems concepts, but these are complex systems. And so, our challenge is, how can we distill it down into a way to say, why should everybody know at least a little bit about operating systems? What is it about? What are the universally kind of applicable ideas that operating systems show us? And there are a lot of them, and it's our job to kind of convey them. And so I think that even if you have some very technical concept, it's possible, like if you explain, the challenge of like explaining how virtual memory works to somebody who knows very little about how a computer works or even programming at all. It's totally possible to do that. I mean, maybe you can't do all the nitty-gritty details that you would if somebody who has more of a technical background, but it's totally possible because there are all these really cool ways to express it using structures that people are already familiar with. So I think that shows that it's even more widely applicable than people may think. And lastly, you can apply it to so many things, and you don't have to be, I think, the expertise in other areas, I think, is a really magical power where you can learn computer science. Maybe you have some, and you can have, your passion really lie in computer science, and that's awesome. But you can also have your passion lie in some other area like political science or environmental science or some other engineering or English or history or whatever it is. And you can uncover all these really cool ways to apply programming and computer science skills to that field. And I've seen some awesome, people at really interesting interdisciplinary intersections of ways that you can apply these things to do stuff that I'm like, wow, that's incredible. Like that's just, the stuff that people are doing. So, you can use it in service of a lot of other things. You can, of course, go into the field and just go into computer science, but there's so many other things that you can use it in service of, that I think is really, really exciting and that people are discovering more and more.
Mm-hmm. Nick, thank you for your time. I really appreciate it.
Yeah, thanks for having me.
Yeah, this was fun. Let's do it again sometime.
Yeah.
All right. See you next time.